monitor being it what are the different vehicles? For example, bus charging tomorrow afternoon session we have Dr. G.P. Amarnath garu. Dr. G.P. Amarnath garu first day చూడండి మనకు afternoon సార్ వచ్చారు. వీరేష్ బాబు NIT వారంగల్ సార్ కి స్టూడెంట్ మాట సార్ సార్ ఫినిష్ హిస్ PhD under the guidance of వీరేష్ బాబు. Amarnath garu he got his BTech degree from ATAL Hyderabad. MTech from IIT Madras and PhD from NIT Warangal. He completes the PhD on fuel cells and simulation of fuel cells using combustion fluid dynamics. So he is much more trained in his PhD. In fact, these students are from GQ. Thank you, sir. Sir presently working in and they are also for DRDO laboratories. There are a lot of laboratories are there. That will explain.
Good afternoon, everyone. So, hope you had a good day in industrialism. Apart from listening continuously, you had a great day. Thank you for raising this. And before I start, I brief about my work, what I do, and I'm here because of that. So I will be explaining. Our company is called Core EF. So it is Core Electronics Technologies. Okay. So our company develops electronic systems for aerospace and defense. Okay, like DRDOs, BEL, NAL, and also. So if you see DRDOs, you have in Hyderabad DRDL, yes, and you have DLRF in Chandragiri, and you have DMDE. Okay, so that is there in Secunderabad. So these kind of labs we support in the sense our company has got two businesses. First business is developing electronic systems. Okay. Second business is distribution of software. So guys, how many of you know about ANSYS? You might have heard about that, right? So our company is one of the company which distribute. It's like we are the channel partners for ANSYS. So ANSYS directly it won't sell in India. So they need some partners. So our company is one of the partners. In that, what we do is we sell the software, and I belong to a technical team where I will be taking care of the problems what I face using the software. Suppose if you take BEL, so they develop electronic systems only. So they face problems like thermal cooling issues. Okay. So at that time, how to solve those problems, or maybe if the problem they know the solution, how to set up in a software, how to validate their experiments, these kind of problems we solve. And so if you heard of NAL, National Aerospace Laboratory, so Aeronautics Laboratory. So here we are supporting for a combustion chamber, and so there we want to optimize the combustion chamber, so for better efficiency. And we also support for what I can say NPOL. So NPOL is in Kochi. So they are having this ranking sonars. So what it means is like that would be this will be fallen under, means dumped on the surface of the sea. So it will track the surroundings. So okay, these kind of physics, how to do in using ANSYS. So that is what we help to the DRDOs. Okay. So just to connect with you, I would like to know how many of you know Fluent. Fluent is an ANSYS software which will be used for CFD analysis, right? So okay, so to better even connect, so how many of you know what do you mean by CFD? CFD, you know CFD? Yeah? CFD means computational fluid dynamics. Yeah. So where you are going to deal with many things like and very important is chemical reactions. Okay. Usually CFD means people think that only flow or thermal and maybe mass flow. Right. So obviously will relate with mass flow. So we also can deal with chemical reactions in CFD. Right? That's where the IC engine is here. Right? So it has got some gaseous flow, right? IC engine. So where you are injecting a maybe liquid fuel, gaseous air. Okay, there you are having a chemical reaction So that you predict using the softwares. Okay. If you want to do that with an experimental setup, I'll tell you how much struggle or how many problems you will be facing. So before that, I'd like to tell you how the user phase. Suppose for general understanding, I'll draw one. Yeah. Consider this as an IC engine, so which has got inlet wall, outlet wall, right? Intake port, exhaust port, and you have a piston, right? And you will be injecting fuel if it is a direct injection system, or if it is a port injection or carburetor, it comes from the inlet, right? This you would do. So what happens if you do the same analysis using a software called Fluent? Fluent will very accurately estimate the flow fields, chemistry also. So what is the problem why we are not using Fluent? And I will propose a new software where you can easily perform all these operations. So for that, how we are going to do that is what we are going to see. Okay. So we have this port, inlet port, suppose. So this port will be moving all the time. Whenever the intake cycle is there, so at that time only it will open. So will the exhaust will open all the time? No. So piston will it be at one place? It will be moving up and down, right? According to the crank angle. We measure that with the crank angle, right? So when you take this, so you need to define the profile how it is moving. So if I consider this as a crank angle, and if I displacement, so at inlet thing it will be moving like this, suppose. So likewise, piston would be moving. Piston would be moving in cyclic manner. Okay, displacement. This is top dead center, bottom dead center. Right? So this would be moving like this, and similarly the exhaust one. So all these are moving parts, right? So if you consider a CFD analysis, you need to have a mesh, right? Mesh is nothing but a dividing of geometry or a region, a domain what you want to consider, what you want to study. So there you are going to divide that into numerous particles. Okay. From that you are going to estimate, okay, whatever the phenomena that will be estimated. So when you have this kind of system where it has got moving parts, okay, with respect to some profile. So what happens is you need to generate a dynamic mesh. Dynamic mesh in the sense. So first is static mesh, which will be same throughout the analysis. So if you consider a pipe, okay, so flow is coming in and it is leaving out. Okay, it can be divided into elements like this. It takes the gradients at this point and it estimates at the next point. Likewise, it estimates till outlet. Right? So this works fine for a simple pipe problem. Whereas here what happens is, so whenever this goes up or down, the mesh has to readjust or construct or collapse. So these kind of problems needs more, what do you say, more expertise. You need to understand the profile. You need to give it as a like C++ coding. Okay, this kind of coding is required. So when that becomes like after doing all this, you never know where the issue happened. Suppose if there is any problem in the solution, you never know where it has gone. So at that time, we have one software called Forte, so which will ask you about directly at what angle to what angle you want to open the inlet port, okay, at what angle to what angle. So you are going to inject the fuel, okay, and piston movement. So these kind of inputs you can directly give it to the software, and you can only concentrate on the these features. Suppose say like type of fuel you want to analyze, or suppose say geometry. So these kind of features only you can think of. And coming to the chemistry here also. So in Fluent, you have the thing called chemical kinetics, right? So if you are aware of this, what you mean by chemical kinetics is, suppose I take an reaction. So methane is reacting with oxygen, and it is giving me CO2 and H2. Okay, simple equation, right? So in real, it won't form directly like this. It will dissociate into number of reactions. Plus, sorry, CH4, CH3. What by M here is M may be any material, metal surface. So when it is reactive, it may react with metal also, and one of the hydrogen is taken by the metal. And this CH3 with the available oxygen, it won't directly form CO2. It may form CO, it may form OH. Okay, there are n number of equations. Okay, you never know how many equations it will be. So sometimes 200 equations, 500 equations. Like that, these equations are called intermediate reactions. So every reaction will be characterized by their Arrhenius constant and rate constant. Okay. If you know this thing, A e power RT, we have seen this, right? What is this called? Rate of reaction. So here you have Arrhenius constant, and R is for rate of reaction. So every reaction will have different constants. So that need to be defined. Then only we can analyze the combustion, right? So having all this, we will see how this can be done and how things can be moved forward with. So this session, what I have planned is, so I will introduce some of the research, what it has been done using the ANSYS Forte software. So after that, we will go and I will introduce the software, how it looks and how you can give the inputs. Those kind of things I will introduce in the second. Okay. So I have collected some literature on spray behavior. When you have a spray direct injection or port fuel injection, how to predict that behavior in an IC engine. So that is what we will see here in that, and piston designs. So if you change the piston designs, how the performance is changing. Okay, very briefly we will see what done. Why I am showing this is it will interest you and it will tell you how many ways are there to do this analysis. So to do that only I am giving these examples. And you have this exhaust gas recirculation, which is being popular for HCCI engines, right? HCCI engines means homogeneous charge compression ignition engines. So that is what people are trying to achieve these days. So in fact, exhaust gas recirculation and low carbon fuels. So even methane, hydrogen, okay. So these kind of fuels, how they can be studied, that we will see. And coming to the next part, I have this Chemkin. Chemkin is nothing but a chemical kinetics software. Yeah. So where we can pull some of the chemical kinetics, okay, and we can import that to Forte. So in Forte, we again I have 3 modules like to means set up an IC engine, and I will show how to analyze the spray behavior. What are these methods available for a spray behavior that I will be showing. And finally, how to do the heat transfer analysis, external heat transfer analysis or internal heat transfer analysis, that I will be showing. As I said, if you want to do an experimental study, so all you need is an ICGen connected with a thermometer, pressure sensors, temperature, correct? Everything you need. And very important thing is the engine should be working, right? Most of the time, this is what will be happening. When I was in so whenever I go to the lab, they say this engine is not working. So first point itself it will fail. So these problems are very much faced in students. So software will give you that freedom to experiment any number of any number of changes. So whatever you want to do, you can do. So I would say garbage in, garbage out. If you want to do any type of experiment, you can do without any changes. When you want to study the spray behavior, so the system will become even more critical. There you need to have a combustion chamber like this, right? And you need to have an opening, which like a see-through. So we need a high-speed camera. So we need, like very precisely we need to capture. Then only we can estimate whether it will happen in like milliseconds, right? So 0.3 seconds, 0.4 seconds, everything will go. So in order to capture those things, we need to have very high precision systems. So it is very difficult to do spray behavior. So how the spray behavior can be studied is not be required. This is useful in the photo also. So here you have a spray. So suppose say from the port it is leaving. So when it is sprayed, it will immediately it will not diverge or diffuse, or it will not do droplets. So initially it will have a region. Okay. So that is called breakup length. Okay. So in the breakup length region, after that you have dispersed particles. Okay. So to analyze this, there are two methods which are included and made as a simple single model. It is called Kelvin-Helmholtz and Rayleigh-Taylor method. Okay. So these two methods, the first region, the region A, breakup length region. So the sketch model will be used. Whereas the other region, the RT model will be used. What like suppose different fuels have different viscosity, different density, right? So these lengths may be different. Okay. So by varying those lengths, also you can estimate accurately. So for that only, to have an idea these models. So I am showing this. So here I have one study where canola biodiesel, right, is being sprayed into ICGen. So this analysis is done in a Forte software. So this is a part of section of the ICGen. So where the fuel is sprayed like this, you can see the temperature of the spray. Okay. Like this, you can estimate the behavior. So it's up to see here you can see one part which is going and hitting on the surface. Okay. And no particles are moved this way. So these kind of estimations you can do. So in this analysis, what they did is, so they have studied the spray where liquid penetration with respect to crank angle being studied, and they compared the results with diesel. Okay, that will give us more meaningful results. What it says is, so the biodiesel, the red color is biodiesel, and the blue color indicates the diesel. Okay, The biodiesel penetration is more compared to the right. Why it is so? Because the biodiesel has got more viscosity, right? So it will take more time to break it. Okay. So same thing. Vapor penetration versus crank angle. Vapor penetration is once it has broken, the droplet has been formed. That droplet need to get vaporized for a proper mix. So in doing so, you can see that biodiesel has got much resistance. It takes more energy or time to vaporize. Okay. And coming to this breakup length, yeah, obvious it is breakup penetration or similar kind of characteristics. Biodiesel will take more breakup length. And coming to droplet mass, okay. So the mass of the droplets also higher in biodiesel because of the viscosity. So these kind of analysis you can do using CFD, right? And these are the usual performance parameters like heat release rate, brake specific fuel consumption, thermal efficiency. Okay, in all this, diesel would outperform biodiesel, right? Outperforms. The why I am showing is you have the scope. You can do biodiesel if you want to do. So you can study those things in this software. How we can do that biodiesels in a software? So biodiesel will not be directly available, that chemical kinetics. Okay, so that is the major challenge what you will be facing if you do this IC engine analysis. So what you would face is, so if you have taken this, suppose this canola biodiesel, so you will never get the direct kinetics file. So what you need to do is digesters. So these compositions you have to choose according to their weightage. So methyl ester may be of more quantity, methyl ester may be of such ratio. So that you need to specify. Then you can pull up that file, chemical file, and you can analyze that. Okay. So this is what we have seen, that breakup length maybe, or even vapor penetration, droplet mass, all these things. In all these things, diesel has outperformed that. Okay. So this is an open source available. So you can go through this paper and you can study that. And the next is like if you want to do analysis timing. Okay. First, we have to see the spray behavior, how far it is going, and how long it is getting evaporated. So, how much time it is taking to evaporate. These kind of features we have seen. So, next we will see injection timing. Okay. So, in this study, what they have taken is they have taken two kinds of injectors. One is having 5 ports and the other is having 6 ports. So, with this, how the injection would be inside the engine. So that is what they want to study. So now here they have considered the SOI means start of injection. We will directly consider this angle, crank angle for simplicity. It is at 625-degree crank angle. Okay, at that angle, see, it is at the bottom edge. It is trying to move towards the top edge. In this phenomenon, you would see that spray, right? So spray is happening this way, and what it red and blue indicates is the lambda. Lambda means equivalence ratio. The fuel richness. Okay. So at this point, this is the profile of that spray. And if you turn to the other direction, in X direction and Y direction, you can see this. Okay. Will this be easily possible with experiments with high-speed cameras? So So it is not possible. It will take much resource. Okay, that will be easily can be done using this software. And the second one is Y plane. Yeah, plus 30 degree. Now after 15 degrees, what happened? Okay, so it's broken up and its side is at like 60 degree. Okay, 15, 30 and 60 directly. So now it has distributed inside the cylinder and near the object center at the time of sparking. So now what happened? It has ignited. So this is how you can estimate how the distribution is. So now if you see this the shape of the piston, hemisphere. So for this shape, this is how it is behaving. Okay, you can also estimate different profiles that I will show. Okay. Yeah, this study also have many features, many studies has been done in this study. So where they are changing the location of the injector also. So these are a lot of as there may be like change of location from at the center to the side positions. So what happened to that? So in that you can directly estimate the the performance of the engine. So here, interestingly, they have injected the hydrogen here, right? And optimal injection timing, okay, which should enhance the fuel distribution and combustion efficiency, leading to improved performance. So that is what they have studied in this analysis. The analysis highlights the critical role of injection timing in achieving stratification and minimizing the emissions. Okay, and the efficient injection has occurred at minus 100 degrees before the degree. Now we have seen spraying behavior, and we have also seen the next one, like position of ports. Now we will see the injection pressure. Injection pressure, how it will affect the performance. So here they have considered the 40% bitumen and 60% diesel blend. Okay. So the other reason why I have considered all these biodiesels is like our interest is of alternate fuels, right? So with respect to that only, I have considered these papers, and where they have means it is possible in using CFD. It is possible. You can study biodiesels also. So I know that biodiesels we can't get the spikes like in this case. So that perception I want to take out of my mind that it is possible. You can analyze any kind of variations. Okay, so that is what I want to show here. Yeah, cylinder pressure is being considered here. After the combustion, once the combustion occurs, the cylinder pressure will increase, right? So if you inject the like fuel at different pressure, what will happen? What exactly will happen? If you increase the pressure, so the breakage, right, break of fuel will be fast, right? That is what is. So the pressure of the inlet is less, means that will make you like more of soot particles coming out of the engine. So that is not expected from an engine, right? So however, and how to know that limitation? Okay, so that limitation you can get through this software, where the pressure is being increased from 400 to 1600 bars at 200 bar intervals, and by increasing the pressure, we can see that the cylinder pressure and apparent heat release rate drop at lower injection pressure. Means it is increasing the heat release release rate is increasing, or the cylinder pressure is increasing. Whereas for 1600, it is reduced. Okay, so it might have reached the optimum position. So that kind of estimation can be done. Yeah, higher injection pressure improves mixing, and mixing improves the combustion. That is what we know. This leads to increased pressure and apparent heat release rate, efficiency, and lowers the emissions. That is what expected, and that is being proved in this study. At very high pressure, so this is this causes the means harm to IC engine, which will create a pressure waves. Okay, so pressure waves may be like so acoustic noise will be higher. So that's why that 1600 bar also not suggested. Okay, and peak cylinder pressure increases with injection pressure. Okay, and as we are increasing the peak means injection pressure, the pressure developed inside the engine also has increased. Alright, and at 1400 bar, the peak pressure was 18.6, which is maximum in the from this analysis. Right, and high pressure may causes early. So you have attained already pressure is there. So the fuel can catch up fire. So self-ignition, auto-ignition, knocking, detonation, these kinds of phenomena could be expected. So to avoid such situations, we need to know the optimum injection pressure, right? And steep pressure rise has been seen at minus 14 degree crank angle for 1400 bar injection. Yes. So that is what at 1400 bar injection. So there has been a steep rise in the pressure, right? For all this, the injection has been started at 22 degree before TDC. Yeah, when the pressure increases, the heat has increased. That will obviously really would be measured to X. Okay. So in the IC inlet, we can have n number of rows where we want to know the temperature. So you can define the monitor and get the temperature, right? So at 400 bar, the peak temperature was 1400. At 1400 bar, it is 1650. So though the temperature difference is of 250 Kelvin only, right? So it may seem less, but it has made a significant change in the performance. Right? So that is what here every 200 bar increase causes a significant temperature rise. But it confirms that injection pressure boosts in cylinder. Right? So that is what we have seen in the injection itself. I could show you the 3 papers, right? So there are any number of papers. So that I may not be able to show you all together now itself. So it's open source so that is what I wanted to tell you. Like you can do this analysis, and industry also wants this. So previously, just I feel like 5 years back, sudden electrical vehicles. So there was a towards electrical vehicles. Now you see the trend. It is declining. Maybe BYD is trying to come back or grow in the market, but there is a fall in the market, and all of out of sudden and nowhere, what Toyota has released hydrogen engine, right? So I wonder how this has happened. How could that engine is sustaining that much temperature? Means what is the temperature it is generating? These things I really want to know. So it is not. Once it gets to the IC, this engines we thought it is absolute, right? So now there is a spark again, and it is showing some feature for the IC engines. And every organization is trying to do that, right? Toyota has did. Will Hyundai will stay calm? No. If Hyundai did that, Kia will stay calm? No. Everyone will try to push towards that. And from there only, we have more opportunities. to go towards the combustion. Right? Yeah. So next we will see some two papers are there. So here I will be presenting about the piston shape. Okay, so there is a baseline means this is a W shape piston. Okay, and you have a straight wall and hemisphere. Okay, these three kinds of piston crowns, it is called crown, right? So the crowns were considered here in this analysis, and also a squish in the sense a radial motion to the fluids. So if it is an inlet squish. So you will have from the inlet air will be coming in the squish, right? If it is an exhaust squish, it will be leaving in the it is a radial velocity, right? So that is what been observed here. And you have a spiral crown and spherical cylinder. So these kind of crowns has been studied in this analysis. Okay. So yeah, this is the first one. The baseline pressure, stride wall pressure, and hemisphere pressure. There is a slight difference between the different crowns. Okay, that is being studied here. And heat release rate also being studied, and which one red is side wall and baseline hemisphere means the performance is almost the same for all of them. So there is a chance that you can study your own design. Okay, so that is what I want to show you here. And yeah, next comes the pressure and side. Okay. Yeah. Now the spiral cylinder is dominating the other piston designs. Okay. So the outcomes of this study are first they have validated this with the baseline. So they have validated and it has showed only 1.97 means 2% deviation with the experimental. And the pressure release means you can also have the pressure sensor inside the cylinder. So that deviation is of only 0.5%, right? And the stride wall piston matches the baseline at 9 megapascal, and hemispherical design shows 2% lower pressure. Okay, just to have an idea. So we are not going to study all this. So they all achieve similar pressures. Yeah, that is what we have seen. And peak release rate exhaust switch by baseline and inlet switch. Okay, and yeah, these are some facts that what they have found from the design. Next comes this means draw my attention more, because this if you see the piston design, so it is like just a flower, right? Flower. Yeah, exactly looks like it. And how would on the earth someone think like it? Right? That is what I am interested in. Like out of nowhere, this was like a simple cylinder. It's being turned to grooves like this. Okay. So these kind of changes for your design you can do, and you can like. If you are BTech in your final year project, you don't do the general studies like simple problems. You try this kind of that will interest you more, and you have much this work in the industry also. So this kind of design being studied here. Yeah. So with this, the temperature distribution, if you see, it is in reverse now. The new design is here, and the old design is here. Yeah. The influence of swirl on the distribution of fuel droplets indicates new geometry exhibits more favorable, right? With the just imparting those kind of grooves, right? Has improved what it has improved, distribution has been improved, right? And the temperature and the fuel spray distribution compared to the this is bit confusing. The temperature distribution seems to be okay in the world itself, right? But if you see the other features, right? So here this is kinetic energy distribution. So till behind, like what were the features we were studying? Heat release rate, right? Pressure, temperature. So out of nowhere, is this study also finds the kinetic energy distribution, right? So kinetic energy distribution also matters. That is what this study shows. So this, for that only this design has been developed, right? The flow rate is more efficiently realized in new geometry, suggested better mixing. So mixing we can expect with the turbulence. So turbulence is related to kinetic energy. Turbulence is related to velocity. Velocity is nothing but kinetic energy, right? So this is how it has given a better distribution of fields. Yeah, swirl ratios has been improved with the both are same. Now coming output apart from the kinetic energy and pressure. So you have reduced the soot by 40% and a slight increase in NOx emissions. Yeah, because of the increase in the turbulence, more what oxygen has been turned to NO, temperature has increased, and enhanced mixture formation led to lower CO and HC, right? So this is what ultimately we would be looking, and that is being achieved with this slight change in the design, right? And you have increased the squeeze rate by 4.2% with the new design. Right? Is this interesting you or making you like not right? Yeah. Making you sleep. Is it making you sleep? I directly go show you this is option. You click here. So that may not interest you. So I wanted to show you some research on this. Okay? So this is an simplest problem. This you can try. You would be very happy to see the results. So what we are doing is we have considered an ICTE again, and in this they were trying to find the heat flux inside the cylinder. Very simplest analysis. So I also surprised with this analysis they could publish a paper means. So how basic level of features did not study. So that will show us the gap, right? So basic feature which is heat flux inside the cylinder that is not in study. And out of nowhere one person has studied features about this. So that means there is a scope. There is a scope to study basic features also. So in this engine, like they are trying to estimate the temperature inside the cylinder. And here there are 6 positions. One on the top, 1, 2, 3, and at the bottom in the center of the cylinder. Okay. Once the combustion happens, what happened is at the point 4 shows the lowest heat flux since the spray target beyond this location. Right? The point 4 is located here. So at that place, the spray is happening. Okay. So there it is observed that heat flux is low. Right? And point 1 near the injector shows the highest heat flux. So that is what unexpected, right? Right? So near the injector, we would think that there will be less heat. But it is near the means in the 4th point, because of the fuel, there is a less temperature. So the spray itself should have lesser temperature, right? But this is reverse. So we never know what is happening inside unless you study it, right? And the point 5 and 6 exhibits higher heat flux compared to the other areas in the piston surface. So 5, 6 are center. If you say for a hemisphere sector, it is in the center of that sector, and 6 is almost near to the wall. So this is like we would expect most of the high temperature in the center. Okay. But here what is happening? That heat is more accumulated near the wall, away from the center, right? So we never know why it is, how it is. Maybe because of the design what they have constructed. Maybe, right? So these may be the phenomena what we need to study. So that what interested me, and I wanted to put this and I will present to you. And most of the heat loss occurs at the piston bowl. Do you understand this? Right? As flame current reaches this. So most of the times what we think, most of the heat will be released or taken away by the cylinder walls. Right? The pins where it would be attached. Cylinder wall, right? If you see an IC engine like a scooter engine or bike, the pins are attached to the side, right? Cylinder, right? So now in this analysis, they have seen that piston bowl is taking the most of the heat. Okay, so this opens up two things for us. One is, we need to distribute more heat to wall also, and the piston need to be more reliable for the temperature. So the material also you can study here. Suppose you have designed a new material which can sustain more temperatures. So that temperature, whether it is sustaining or not, how would you test that? You can test this way. Okay. Yeah. And the results from that study also, like in cylinder pressure and heat release rates were almost closely matching with the experimental data. And the model accurately captures the cool flame and main heat release locations, right? Contour plot showed predicted temperature and heat flux distributions, right? And predicted heat flux near the piston head and both are compared, right? That is what they have done. We have seen the graphs. Peak heat flux value fall within the typical diesel combustion measurement range. Okay. For this fuel, it is different compared to the diesel, right? So piston design also matters, right? And also heat flux, basic study like heat flux, how much heat, how much temperature. So this kind of analysis also you can do for your projects or for your research, and there is a much scope for your paper to be published, right? Right. And now I have another paper. So there are only two papers. So after this we will take a break. So exhaust gas recirculation, you all know what it is and why it is required. The auto-ignition timing or the start of combustion in HCCI engine is what is determined by reactivity of the mixture, and which can change by modification of fuel blendings or exhaust gas recirculation. So what happens is when you run the engine faster, okay, so there is a much scope for higher temperatures. So that temperatures will lead to formation of NOx, right? Higher temperature will lead to NOx. That is the common. So these NOx, to reduce that NOx, what people are doing is they are circulating some of the exhaust gas into the cylinder again. So that will reduce the attainment of highest temperature, right? So that is being tried and that is successful, right? And these are promising technology, especially for HCCI engines, as I said. So that would delay the auto ignition timing. What it do is it will delay the auto ignition timing, and by affecting the chemical reaction and leading to reduced heat release rate, and automatically it will reduce NOx, right? So that is what, with a different percentage of EGR. So in the experiments, you imagine how you can do this, how it is possible. To measure you how much exhaust has come and how much you want to recirculate, how is it feasible? So it takes, maybe it is possible obviously, but it takes time and much resource. So that is very much possible, and simply you can do using this software. Here, no easier, 10%, 20%, 30% easier is being circulated into the engine again. And these are the performance curves what we see. Yeah, first one is in cylinder pressure, and then current heat release rate, and then in cylinder temperature, pressure, temperature, heat, all same. And coming to the, what is this? Duration. No, sorry. 10 to 90% heat release rate. Heat release duration. Okay, with respect to percentages. So that is being studied. So this is also a new parameter. What they have said. This all we have seen already. And this is a new parameter. Right? Yeah. Okay. So the up to what percentage? 98% reduction in NOx is achieved with the slight increase in CO. So you can get the result of it. Either we will have more NOx or some CO. So it is obvious. Yeah, it can, like shorter combustion duration leads to high thermal efficiency. The final paper for this one. So here what they are doing is lower carbon fuels like methane and coke oven gas. Maybe like some it is called coke oven gas COG and H2 has been considered for this one. And basic same all the kinds of analysis being done, temperature, pressure. So here they have operated with 2009 and they have also varied the equivalence ratio from 1 to 2. Okay. And they have seen this performance and validation. So in the first graph, what it says is it is a validation. Okay. If directly methane or coke oven gas has been done experiments, so how much deviation it is there. So for CH4, there was a much deviation at lambda is equal to 1. Air fuel ratio 1. Okay, and here at 1.5, it is slightly better, and here it is not considered. At 2, it is very difficult for methane. So that is being studied here. And coming to the wall heat transfer. So this is also a new parameter and chemical heat release. So new parameters, like whenever I see new parameters, I will use interest you. So here also, like in the experimental validation itself, you can observe one thing, that the amount of energy what they are releasing, that is higher at lambda is equal to 1. Okay, air fuel ratio and stoichiometric ratio, it is better compared to what? Okay, you can directly relate, just draw a line, right? Okay, that itself will tell you that the stoichiometric ratio is better compared to the other for this analysis. And coming to the chemical heat release rate, so the methane has got highest, right? So this heat release rate has been estimated in terms of joules. It is in joules, right? And these are regular, like temperature, pressure at different RPMs. And been studied. And there is a score, we can vary the RPM. Okay. Till now, what we have seen, no RPM was there. Okay. So this is how it is different from the previous. So in what I can say, that the ANSYS Forte allows you to have continuous tracking. Okay. Like maybe through having different regions, points, surfaces, or where you can have, you can estimate the average pressure, temperature, apparent heat release, or you name it. All the parameters, whatever we have studied. So all these parameters can be studied, and so that the chemical inputs are also available in this software, and you can readily use them. Right? Any questions on this? Okay, we'll quickly have a quick break for 10 minutes. Yeah? So we'll come back and we'll see about this.